I hope
Well,
you're
great.
well.
Well, thanks for having me. It's certainly great to be back and talk to this group. And we've had some great webinars in the past. And you know, one of the things that I think is very important when we talk about transformers and other very expensive assets in the power in the power system, and that is that extend life extension of critical assets is becoming more and more important to us as the not only the price of assets such as transformers and breakers have started to skyrocket, but also based on lead times. To try and source a new transformer these days, I don't know if any of you have had the pleasure of trying to do that, but depending on the size and type of transformer, you could be out 3 to 4 years in ordering a new transformer. So life extension becomes very, very important, and things that we can control. And as Mark said, heat is not a good thing in any power system. And as you can see, this one's very hot. But one of the things that we want to do is we want to do everything we can to try and avoid failure, especially catastrophic failure, which can be extremely costly, not only in terms of that asset, but its surrounding assets that can be affected by such an event. So if we talk about transformer failure, there are certain categories. The three main categories are electrical failures, mechanical, and insulation. Basically, it falls into those three basic categories. But if you look at the chart, there are certain failure points that really seem to stand out, and historically that has been true. Onload tap changers is, of course, one of them, as the only moving part in a transformer, really, and subjected to a lot of transient currents. These things have a tendency to fail. The other is, and most of us know this, and any type of bushings that you have, basically a good transformer that's well taken care of. We've seen some that are 50, 60 years old at this point, and the life extension of these and life expectancy has really gone way past what their intended design was. But when you talk about bushings, it's very, very important to understand that at some point in time during the life of that transformer, they're going to fail maybe 2 or 3 times or need to be replaced. And so, when do we do that? What type of insights do we have in terms of when we need to replace a bushing? So these things are all very important in terms of understanding when and how we're going to diagnose the health of these assets. Well, the first thing I want to discuss, and I've talked about this before, I make a big point of this because this is very, very, very important in terms of extending the life of a transformer. And that is in the insulation system. Three things that are really accelerate the aging are heat, oxygen, and moisture. And of course, heat refers to loading. Where you have the greater load, you have hotter the transformer's insulation system is going to be. And then also heat can come from the result of poor cooling systems, faulty radiators, or some outside electrical conditions, such as volts per hertz conditions, that can really heat up the windings of the transformer. But one of the things that we can certainly control is moisture. Well, where does moisture come from? Well, moisture can be present during the manufacturing or the final assembly process. Now, generally, okay, they'll take the transformer, just the windings themselves, put them in a vapor phase chamber and dry the insulation. It's like an oven. It just cooks it and then, draws the moisture out. So you start with dry insulation. But what happens after that? Well, it gets put in a tank, it gets transported, via rail or a flatbed and delivered to the customer. At that point, they'll attach the radiators, they'll attach the bushings, they'll fill it with oil, and there's always a chance that you can get water going into the transformer tank during those processes. The other is leaky gaskets or around the bushings or the radiators. You know that whenever you have mineral oil leaking out of the transformer, you know for sure moisture is going in. So that's very important to be aware of. Transformer designs such as free breathing conservator. And we see this down here. If we look at the desiccant right here, if the desiccant isn't working properly and we don't have a good nitrogen blanket, water from the atmosphere can become an issue. And then any kind of maintenance that you do on bushings or bushing replacements. If you do this type of a replacement during the rainy season or when you got bad weather, water can get in there. I've also seen bushing replacements that were done improperly, where they weren't seeded right, and the first rain that came along just dumped water right into the tank. But the one thing that I think that's most important to understand, moisture comes from the natural aging of the insulating system itself. So what happens is, the solid insulation is made up of paper and pressboard and also polymers and cellulose in the cellulose paper. And we have to make sure that it has a good, what we call degree of polymerization or DP. And that's the strength of the insulating paper that's in the transformer itself. And a good, healthy, brand new transformer has a measured DP rating of around 1800. Well, as the transformer starts to age, naturally, the resin bonds surrounding the insulation start to break apart and they start to kind of degrade as your degree of polymerization goes down. When these resin bonds and these molecules split, the byproduct is moisture, is water. So, even though you've never exposed that transformer to outside moisture, it can generate through its natural aging. So we know that the life expectancy, this chart on the side of your screen is called the Lungard chart, and that's part of IEEE C5712. And basically, this shows the life expectancy of the transformer based on temperature and the life expectancy of it based on moisture content in percentage. That's percentage in the insulating paper. So you can see that the hotter the temperature and the greater the moisture content is, it has a dramatic effect on the life expectancy of the insulating system. So what IEEE tells us is that, you must take care of moisture. You must do what you have to mitigate moisture in the transformer based on these levels. And in terms of ppm in your oil sample, depending on the size of the transformer, you can see the limits here. But what we really want to be concerned is the equivalent water content in the paper itself, because that's where it does the most damage. Okay, so in a brand new transformer, and I mentioned this earlier, okay, that brand new transformers have to be either based on their size, no more than 0.5% or 0.8% by weight in terms of the moisture contained in there. And if we were to check the moisture in the insulating system on a new transformer, let's say we had a fairly sizable transformer, in this case 450 MVA, at 2% water, that would mean we would have to extract almost 99 gallons out of the transformer itself in order for it to meet industry standard for a new transformer. A lot of people don't think about this. They think they got a brand new transformer, they do their routine commissioning tests, and never even look to see how much moisture might be present in that insulation from the time it leaves the factory to the time we get it put in service. And why is moisture bad? Well, what happens when you have moisture in your insulation is it lowers the bubbling point in the transformer. And this bubbling, okay, creates voids in the insulation. It results in partial discharge, and that can lead to excessive deterioration of the insulating paper. And once you damage that paper, okay, that damage is irreversible. Okay, so to summarize that, the moisture just embeds itself in the voids of the paper, creating partial discharge, and that'll cause a carbonization. And you can see here that that'll create this treeing effect and eventually lead to complete breakdown of the insulation that you see in this particular picture. And here's just an example of certain failures that we had in the insulation because of excessive moisture. So what do we do? Well, the title of the paper was Advanced Diagnostic Capabilities, and we do have advanced capabilities in terms of detecting and calculating the amount of moisture in the transformer. So the very first thing that people have relied on is, of course, doing your power factor measurement. And then power factor measurement, if you see an increase in your power factor, that means you have some type of a deterioration in the insulating system. That can be either moisture or carbonization or other forms of contaminants in the windings, and of course in your bushings. So, this is a fundamental test. We've been doing it for years, and basically what it's telling you is the overall health of the insulating system itself. And it's sensitive to aging, moisture, and contamination. But there's one problem with that, is that it represents just an average condition of the total insulating system under test. And we don't know by looking at those test results whether it's just general and uniform deterioration or if we have a localized area of severe deterioration. And it's impossible to differentiate and characterize losses, which may be moisture, aging, contamination, again, oil conductivity, or some combination thereof. So the first advanced technique I'd like to talk about is extending your power factor range, not just at 60 hertz, which we all test at in terms of measuring power factor, but also extending that frequency range either from 10 or 0 up to 400 hertz. And the one thing that I want to emphasize when we say advanced testing, it doesn't mean it's more complicated. There's plenty of testing assets out there that have the technology to do this without adding extra, knowledge or training or extra time involved. So, but what does this do? Well, when we extend that range, it gives us some additional information to reveal what we refer to as the blind spots. It puts an emphasis on what we call conductive losses. Now, conductive losses can be a couple of different things. It could be sludge, it could be furans or inert ingredients, okay, but it can also represent moisture. So if we look at the lower values of the power factor below 60 hertz, if we see that these are lower in terms of your power factor measurement, that most likely indicates that we do not have any conductive losses. And if that coincides with your oil screen, your DGA results in terms of your ppm measurement, you're good to go. It's with all certainty, you really don't have a moisture issue in the transformer itself. So if we look at an actual test here, this would be a measurement of transformer with a dry winding insulation. Okay, and you'll notice that below this 60 hertz value, it's coming in at a lower value. Okay, now, does it matter how much lower? Not really. It's really the angle of which, those measurements are coming through that 60 hertz measurement. Okay, now, if we have higher values of power factor, okay, that would indicate conductive losses. But again, this could be sludge in the oil, it could be furans, but it could also be moisture. Now, let's say that your dissolved gas analysis shows an elevated amount of moisture. Okay, it shows a high ppm measurement. And let's say that your power factor also shows that you have conductive losses. Well, you could very well have a moisture issue. Okay, but we're going to take this testing one step further in terms of how we're going to really get a good indication. Okay, so let's take a look at this. Now, you'll see here we measured this transformer at 60 hertz and it all looked identical. But when we change and change our frequency indication, you'll look one transformer A much higher, transformer B much lower. But again, you'll notice at 60 hertz, you don't see much difference here. Okay, when we do a test called dielectric frequency response, one transformer is coming in at 1%, the other is 3.4. Now, what that indicates in terms of the age of the transformer is quite significant. Okay, the age expectancy of transformer B with the drier insulation, you've got 100 plus years at less than 70 degrees C operating temperature. The other transformer, not so good. Maybe 10, 15 years in terms of its life expectancy. Now, if you start to increase that temperature, those numbers get even worse. Okay, now what is the problem with getting an actual or good measurement of the moisture content in the insulation? Well, what we know is that when you take a transformer offline and it starts to cool down, the water moves from the oil back into the insulation and it hides in little areas, little pockets in the solid insulation, spacers and barriers. And what happens is that creates inaccuracies in terms of what we measure in our ppm. So this is why we apply typically for many, many years what we call equilibrium curves. And that means that we take the oil temperature when we take the sample and we record that and supply that with our DGA analysis. And then the lab will try and estimate what the actual moisture content is with that temperature correction. But there's a lot of problems associated with that. The problems associated with the fact that um, you could have a bad sample. Okay. Let's say that you took your DGA, you took your sample, you sent it off to the lab, and you had a high level of ppm. Okay. Now, in a lot of cases, if you're a testing company and you show that to the customer, they say, "Oh no, I've got to mitigate this moisture. Let's perform a dry out process." Well, you may be doing that needlessly, because you just took a bad sample. Okay, and there's a lot of reasons for taking bad samples. You didn't draw off enough oil. You had moisture ingress from the time you took the sample to the laboratory. It doesn't take much to create a distortion. There was a period of time where we went out, we did an experiment. We went to a transformer, we drew off 5 oil samples, sent them all off to 5 different labs. The ppm measurements that came back were dramatically different. Okay, so what do we do in terms of good moisture analysis? Now, the one point I want to make here, that doing this extended power factor measurement is also relevant to oil filled bushings. Okay, so once you have the ability to take your C1 test and actually extend down that frequency like we did before, you can actually see an indication of moisture in the bushings themselves. And that's one of the most damaging things to bushings, to OIP bushings, that there is. I mean, when you test bushings, you do your visual inspection. You might have, like Mark said, you might check for heat. You might take a thermal measurement and look for excessive heat in the bushings while the transformer's online. But basically, you do your C1 test, your C2 test, or a hot collar test, and you compare that to the nameplate rating. Or if you don't, on a C2 test, if you don't have the nameplate data, you compare one to the other. But when you drive that frequency down, you can see here, okay, this is C1 measurements, where on some of the bushings, 2 of the bushings, you'll see an indication of conductive losses in the bushings themselves. So you can run this test on bushings also. Now, there's a couple of ways to check for moisture levels, and of course, this is measurement in the oil, and we know that this can be somewhat inaccurate and may even give you false indication on a more higher level. Okay, so what is the new technology that we use? Well, around 1997, the University of Stuttgart came out with a process called frequency domain spectroscopy. Well, they changed the name to dielectric frequency response because it's much easier to say in terms of being a tongue twister. But basically what it is, it's a power factor or tangent delta measurement over an extremely wide frequency. And what they did was they took, under laboratory conditions, they knew how much moisture in percentage they embedded into these samples, and then ran this test on them to see what the geometry of the response of that curve looked like under certain conditions. And it was pretty amazing how accurate it was in terms of looking at the model that it produced in these curves and equating that to the moisture percentage in the solid insulation. So this was quickly accepted into industry standards by both CGRE and IEEE. There's been IEEE working groups on the Transformers Committee, which I've been on for about 8 years, and they have really narrowed down the modeling to be actually very, very accurate in terms of determining the percentage of moisture in the insulation. It's a very simple test to run. It's one test where they again capture the power factor measurement from a very, very low frequency up to a very high frequency, and then plots the curve right here. This is your power factor and this is your frequency. And by looking at the geometry of the shape of these curves can tell you exactly what the moisture content is. And there's no super analysis that you would have to do as an operator. The software all does that for you. So this is a very accurate test to run. Well, lo and behold, we can also do this test on bushings. So you get a much more accurate percentage of how much moisture is in your oil fill bushing. Okay, and again, this is all done in terms of number one for bushings, helping you determine when it's a good time to replace those bushings before you have catastrophic failure, or number two, being able to accurately determine if you need to mitigate the moisture in your transformer. Okay, so the next thing I want to discuss, and this is more of in line with mechanical failures, and that is talking about transformer through faults. Now, through fault currents, there's a number of reasons that you have mechanical failure in transformers. And the one we always think about is, of course, transporting. You transport that transformer from the factory out into the field and you get ready to commission it. And you might do an SFRA test to make sure that no winding deformation or buckling or anything like that happened during the transportation. But you can also get, this type of mechanical failure from seismic activity. Maybe if it's a GSU where you have improper synchronizing, it creates a lot of mechanical stress on the windings. But the one that I think is most overlooked are through faults. So, what is a through fault? Well, that's when the transformer experiences current flowing through the primary and the secondary windings equally because you've had a fault either on the line or on the bus where the transformer is connected to. Now, this will not cause your protective relays, especially your differential, to trip because the current's equal going through. It's just a much higher value. Back in the days when they first published standards for transformers, the big thing was thermal limits. Okay, and that's basically a guide as to how much thermal capabilities a transformer would have. Well, soon after that, they discovered that it's going to be important for us to look at transients. What kind of transients can it stand in terms of multiples of base current rating? So, through faults can of course be very damaging. Now, they're more damaging in terms of the how the core design is, because typically they're more damaging to core form rather than a shell form, just due to the multiple current channels that a shell form has. That's not to say that a good strong through fault or multiple through faults could not damage shell type, but it is more damaging typically to core form type transformers. So, they can vary greatly across short spans of any electrical grid, whether it's distribution or overhead transmission lines. These are generally the result of a low impedance path to the ground being introduced into the circuit, such as dielectric failure of protection equipment or tree limbs striking overhead lines that can cause current to exceed the transformer's base rating. Any slow or malfunctioning breakers, breaker failure that doesn't clear a through fault, quick enough can intensify the possible damage of the transformer itself. So, how do we know when a through fault has happened? Well, I talked to my friends in the relaying groups, and one of them from Schweitzer Engineering that I'm close friends with, who kind of specializes in transformer protection, says, Drew, that most of your protective relays on a transformer, your digitals, have through fault monitors on them, where they look at the through fault occurrences and capture the magnitude, the date and time when it happened, how long the fault was there. He said, as far as he knew, he thought maybe about 80% of those that set the relays never enable the through fault monitor. So how would you ever know that you had a through fault unless you incorporate the through fault monitor, which is just looking at these events, and if they're high enough or exceed the rating of the transformer, will simply alarm. This isn't an element that's going to trip your transformer offline because it may just be a quick transient, but it's very, very important. You can see here in this sample report, and of course, this is the relay software giving you this data, and it's a little bit fuzzy, but you'll see that it shows you, the three phases of where they may have occurred, the magnitude in terms of how much current, and then the date and time. Because what's important to know is that one single through fault, while may not damage the transformer, if they're reoccurring continuously, it puts continuous stress. So how do we set a transformer? How do we set these through fault monitors? Well, it's not very difficult, really. And you can also always refer to your transformer OEM or your protection engineer that's working on this. But basically, it's just a single calculation of the transformer's rating, secondary voltage, the percentage of impedance, and this will actually give you a basis for how to set a through fault monitor. And you see, it really depends on what category of transformer it is based on the MVA rating. So, but you can see that they're all fairly similar in terms of when it's going to alarm, in terms of the time and the times the base current that transformer is rated for. All right, so let's say we've had a number of through faults and we've recorded this information, and we want to actually, during our next maintenance period when we're testing the transformer, see if there has been any physical damage associated with the transformer. And there's two types of tests you run for looking at mechanical failures. One, of course, is the SFRA, sweep frequency response analysis, and the other is your leakage reactance test. And the IEEE guide C57149, which is interpreting frequency response analysis, and C57152, which is simply your guide for diagnostic field testing of fluid filled transformers. And by the way, both of these guides are in revision right now and being updated through the IEEE Transformers Committee. But certainly both have good guidance and understanding. Now, what does sweep frequency response analysis look for? Well, it looks for core movements, faulty ground, core grounds, winding deformation, displacements, all sorts of physical, mechanical issues that you have within the transformer itself. And you can see some examples of this on the side. Well, one of the things that we know when you do an SFRA test is, depending on where you see the abnormalities, it can kind of pinpoint exactly where that might be. In the lower range, it could indicate a problem in the core. In the middle range, it's the interaction between the windings, and then the winding structure influences in your higher range. Well, one of the things that we do know, okay, and again, this is in C57149, is that if you have a physical damage based on a high through fault or a series of through faults, that's generally going to be associated with your low voltage winding in the form of radial deformation. So your diagnostic focus for your SFRA will be your low voltage open circuit test and your high voltage to low voltage short circuit responses. And again, this is all documented in the IEEE document. Now, the other test you can perform, and this is much simpler, okay, is leakage reactance. Now, I'm sure, or otherwise known as short circuit impedance. And I know that if you work for a contract testing company, and I know because we rent to them all the time, we'll rent a power factor test set, and then every once in a while, the leakage reactance accessory with it. And sometimes if you ask a field tech, well, why do you need to do a leakage reactance test? The response might be because my customer wants it. Well, I have an old saying that says you really shouldn't do anything unless you understand why you're doing it. And it's important to understand why and when to do a leakage reactance test. Now, there's typically two two parts to this test. One is a three-phase equivalent where we're going to measure the impedance of the transformer on all three phases and calculate what that impedance is. Okay, and if that impedance is greater than 3% what's stamped on the nameplate, we have a problem. But then we're also going to do a per phase test. We're going to measure the impedance of each phase independently and compare that with each of the other phases to make sure they're within in 2%. Now, what are we actually doing? Well, we're looking for leakage flux. That's why we call it leakage reactance. Flux measured in terms of impedance of the transformer. Let's take an example. Let's say you have a wooden trough running downhill, okay, and there's water in the trough and it's flowing downhill, and naturally from top to bottom you'll have a little bit of that water spill out, and that'll be your leakage. Well, transformer has a certain amount of normal leakage flux within the core and the windings. Well, let's say you take a rock and you put it in the middle of that trough. You're going to have a lot more leakage, aren't you? Okay, and that's the same thing. When you have physical displacement in your windings, it's going to affect your leakage reactance test and be measured in terms of impedance. But it's very important to understand where to find, on your transformer nameplate, what that impedance is. It's always stamped at the factory, and that's what you want to compare your results to. Okay, and here's just a simple diagram that you're going to run. Now, these tests aren't difficult to run. In fact, if you have some multifunction transformer test set like a Mega or an Omicron, or even the accessory to the Doble M4000, you can run this test very easily. It's not that difficult. And why should we run it? Well, there's a number of reasons. Number one, if you have a through fault monitor and you've seen a number of occurrences between the testing intervals, then you'll want to run a leakage reactance test. It's your first indication that you may have physical damage. The other is, what if you don't have a monitor on there? You don't know if you've had through faults or not. Well, probably a good idea to incorporate a leakage reactance test. And you can see here, this is a normal calculation of how we get the three-phase equivalent. And again, comparing that to the nameplate impedance measurement. And this, again, is your expected results. That three-phase equivalent should be plus or minus 3% of the nameplate, and per phase should be within 3% of the other values, the other phases. Okay, so again, here's when we're going to perform it. We could always do it when we're commissioning the transformer. We can do it when your through fault monitor is recorded. Anytime we suspect there may be some physical damage to the windings. Now, if you see an indication, okay, based on those standards, then you'll want to do your SFRA, because that is really the fine tune in terms of finding mechanical damage. Now, here's just a case study on a 50 MVA transformer where they went out and the very first thing they did was that they ran their power factor test, and at 10 kV, it wouldn't even run. So they lowered it to 7 kV, and the power factor was almost 50%. Now that we know is totally unacceptable. Well, then they looked at the dissolved gas analysis. And the one thing you'll notice here is that, of course, this is historical analysis over time. Everything seems to be normal until they get to this test, and you can see the acetylene went from 0 up to 21. And that is a serious indication that we got a problem. Okay, now here's the leakage reactance test results, and you'll see that the three-phase equivalent was well within that 3%, okay, right here. But when we did the per phase, you could see that B phase clearly has an issue. Okay, then we looked at the SFRE results, and you could see that the high impedance fault on phase B of the low voltage winding, clear indication during this test right here. And this is kind of what it looked like when they tore the transformer apart. It certainly wasn't pretty. And again, that was, they didn't even look at it or consider that the problem existed until the differential relay tripped. Okay, and this would certainly create a differential trip. So one of the key elements that we can do when we're doing a with your test set um, is that we have the ability to do what is called as frequency response of stray losses. Now it's run exactly the same way as leakage reactance. So what frequency response of stray losses is Hydro-Quebec back in the 70s was looking for some additional tests they may use in in addition to SFRA to see if they could find some conductive losses or some mechanical deformation. But they really didn't have what they were doing was they were taking the frequency and running it up to 400 hertz and measuring not just the entire impedance, but just the resistive value, okay, that they were seeing at these higher frequencies. And they do this between phases. And what they were seeing is pretty interesting, where we're looking for mechanical failures with leakage reactants with frequency responsive stray losses. What we're looking for is an electrical possible electrical failure with what's called a shorted conductor bundle. Now, this is done again, just measuring the resistance, okay, of the impedance in per phase on each of the three phases. So what happens when we apply a higher frequency? Well, we get back to the basics of how electricity moves through a conductor, and you'll know that when you apply DC current, it goes through the entire surface of the conductor. When we start to put on AC, okay, we get what's called a skin effect, and that is that the current only flows through this outer portion. And that's referred to the skin depth. So with a typical 60 hertz signal, that skin depth is reduced by about 63%. So it's only traveling over that entire band. Now, how can we get that skin effect to be more pronounced? Well, as we raise the frequency, okay, it's naturally going to raise the resistance that we measure from that conductor. Okay, so as the diameter increases, the skin effect becomes more pronounced, and our measured resistance is also going to increase. Now, the way we build the windings of the transformer, it's not a solid conductor wrapped around the core. It's a series of conductor bundles with insulation in between each one of those little conductor strands. Okay, and the one on the right is probably um, more like what we see here in North America, where you have these flat conductors and there's insulation in each one of those layers. Well, what happens either from manufacturing defect or some failure over time if these little strands start to short up against each other? Okay, now that's what we refer to as a shorted conductor bundle. Okay, now here's the thing about that. This could be part of a manufacturing defect that probably was never checked at the factory, and they probably never ran this test when they commissioned the transformer. And it's probably, well, it's definitely not going to show up on any normal electrical test that you do on a transformer. This is the only test that will indicate this problem. Okay, and eventually could lead to a hot spot and eventually be an electrical, you know, uh, look at an electrical failure in the transformer itself. So here's what it looks like normally. All three phases you can see have some good symmetry to them. They all follow the same measured resistance from that 10 to 50 hertz to 400 hertz. Okay, now we see right here, you'll see C phase looks much higher than the other two phases. Okay, so this is an actual case study. When we tore the transformer apart, okay, this is what happened. This is local overheating due to a shorted conductor bundle. Now, if I go back to this previous slide, this will show you or give you some interpretation of when you should be concerned in terms of the deviation between the three strands. So anything greater than 15% difference in the measured resistance between the strand is probably going to indicate that you have a serious problem or you have this shorted conductor bundle. So when should I do frequency response of stray losses? Well, since it's possible that the bundle can be related to manufacturing defects, it should most definitely be a part of your commissioning process. And many of these are just a little tiny checkbox in your test equipment that says perform FRSL. You might have seen that before, not known what it is, but that's what this is. If your transformer is showing any kinds of gassing, such as hydrogen or others, and all your tests seem normal, this might be a good idea to run. If leakage reactance is part of the routine test, just check that box. It doesn't take, but another minute to perform and can certainly provide more information. Okay, now finally, just to wrap things up, one of the weak points we talked about is the on-load tap changer. Malfunctions in the mechanical switching, high resistance contacts, and overheating, contamination of insulating oil, can all lead to failure of your on-load tap changer. And a couple of the new industry standards in terms of advanced testing. This comes from the Transformers Committee C57-152, Section 7.4. This is the Guide to Field Testing, addresses some new approaches to testing and validating the health of your on-load tap changers. One is a vibroacoustic measurement, and that is as you move the transformer, from one position to the next, having these little vibroacoustic sensors on the tank that actually measures and records the vibration and the amount of the acoustics. And if some are, higher than others, it's going to give you investigate further. The vibroacoustic measurements are one of them. It's actually very easy to run depending on the equipment you have, and how easy the access the cabinet is. The other thing we can do is we can measure the motor current of the LTC. Is the motor, if you have any contacts there that are binding, that's going to drive the current of the actual motor, turning the tap changer up and record to be higher. Now, the other one that really people are paying attention to is what we call dynamic resistance measurement, and that is while you're actually performing your DC winding resistance, instead of turning off the DC between each one of the tap movements, you keep it in place, and then you look at the transient and you record the transient current as it's going from one tap to the next, and they should all be uniform. If not, then you probably have a problem. And basically, this is just the look of an aged diverter switch that over time, because of the arcing and sparking going on with LTCs under normal operation, of course, you can also, if your cabinet is separate from the actual transformer, you can also do a DGA analysis of the oil on the OLTC as well. But you have to keep in mind, you're not going to analyze that sample the same as you would a normal oil in the main tank, and that's because you have natural gassing that's going to occur because of all the arcing and sparking that's going on normally. So your analysis has to be a little bit different in terms of comparing this to what you see in the transformer. So with that in mind, Randy, I will take any questions at this point that may have come up from this presentation.
Okay, thanks very much, Drew. Good presentation, as always. Thank you. I have a couple of comments and a few questions. One of them, at the beginning of your presentation, you mentioned how there was a long wait time for transformers to be manufactured. And when I was with the California Department of Water Resources a few months ago, they mentioned to me that they needed to purchase transformers and put them into storage because they realized what a long wait time there is for transformers to be manufactured.
Yep.
And so what a lot of utilities and large transformer owners are doing is they're purchasing and storing them. So it's like hoarding for when
Well,
there's
yeah, and that's true, Randy, but we see that more for dry type and distribution, pad mount, smaller transformers.
yeah.
It gets really, really expensive and economically difficult when you try and do that with say a 40 MVA transformer. But
Well,
yeah, it's important to, keeping spares is, and I guess that would drive the lead times up further if
that's
everybody's
right.
ordering two instead of one.
It contributes to the problem. Okay.
Yep.
All right. is there a relationship between the typical age of a transformer and its failure rate?
Um, well, that's one of the things that we're trying to address here, because a lot of that has to do with how you maintain, what kind of conditions you operate that transformer over. You can have some transformers fail within 10 years.
Okay.
You can have some that last 60 to 70.
Mhm.
And moisture, heat, and oxygen have
Okay.
much to do with that. It's like owning a new car. If you take your car and you run it pedal to the metal 24/7, and you're going uphill in a low gear and putting a lot of stress on the engine and the transmission, it's not going to last the same way as if you baby it and you change the oil all the time, and
Yeah.
you keep your maintenance up.
You mentioned moisture. One of the first questions that we have is about moisture. Is there a
Mhm.
solution to minimize moisture,
Yes, there is. And
such as the prevent the damage by
mhm.
installing heaters with thermostats inside the transformer to prevent humidity?
Well, yeah, that's really not that effective. And
Hmm.
the thing of it is, the very first thing you need to do is have a good indication of how much moisture you have in the transformer. And the sooner you mitigate any excessive moisture, the better. And there's a lot of methods to do that. And of course, you take the transformer offline, you can have the oil processed, you can bring in a processing truck, do a hot oil spray, pull a vacuum. But there isn't a one other solution that we actually rent, and that's called the Trojan dryout system. And this actually dries and filters the oil, processes the oil as the transformer's online. And the benefit to this is that by having the transformer still online, you're at operating temperature at equilibrium, meaning the moisture and the insulation in the oil is equal. And as you're drawing the water out of the oil, you're also pulling it out of the insulation. So it's very, very effective, especially if you can't take your transformer offline to do the processing, if it's a critical asset. So,
Yeah.
the fact of the matter is, the sooner you address and mitigate moisture issues, the better off you're going to be in keeping that from reaching premature failure levels.
I've wondered for some time whether or not, after all these years, there wasn't a better material to use than cellulose for
Well,
insulation.
well, unfortunately not.
Or is it just
um,
there is a material, but it's just too expensive? Or is there?
Yeah, price it's the same with the difference between mineral oil and natural esters such as FR3. And I'm glad you brought that up,
Yeah.
because a lot of people try and equate and test and analyze FR3 and other natural esters to mineral oil, and their properties are considerably different.
Hmm.
Where if you had a 200 ppm measurement with mineral oil, you'd be raising a red flag in a panic, going, "I got to get this thing dried out." With natural esters, FR3, you could have a 200, 300 ppm and have no concern whatsoever, because it's
Hmm.
such a dry, it protects the insulation that much better. But again, it's a matter of economics. It's much more expensive, but it is getting much more much more popular in terms of a replacement or ordering things like FR3 when you buy a new transformer. But
All
the,
right.
the, the whole game changes. Your
That's right.
power factor is going to be elevated. Your winding resistance is going to come down. You'll look at your results and go, "My gosh, what's going on here?" Well, it's different insulating
Right.
properties.
Okay. Next question. Devinder wanted to know your thoughts on sound level and RIV tests criteria.
For transformers, yes, there is an IEEE guide. In fact, there's a revision being going on right now, and I know I sound like a broken record when it says all these published standards are being revised, but you have to understand, we're on the Transformers Committee, we're required to revise them every 10 years. And since it can take 5 or 6 years to finish a revision, you got to start early.
Hmm.
But yes, there are acoustic level criteria for transformers. Noise is not a good thing, or excessive noise is not a good thing. Vibration can indicate that you may have a problem. And if you do see an increase in acoustic levels, it's always a good idea to, get your maintenance testing underway to see if there's any issues. A DGA, your power factor, your TTR, your winding resistance, excitation. Excitation current is one thing you want to look closely at if you're getting excessive noise in a transformer, because that indicates a problem in the core.
Okay, next question from Christopher. Have you ever seen this bundle testing failure? And if so, is it common? Is the related test identified in the NETA testing standards for testing?
No, it's not in NETA. In fact, I'm on the standards review committee for NETA, and we just had an update. And yeah, the review committee decided they didn't want to address it at this point. Is it common? No, it's not common. Is it easy to test for? Yes, it is. Has it happened? It certainly has. I showed an example of that. It's just a one little piece of insurance to make sure that you didn't have a manufacturing issue. They typically won't do it for a factory acceptance test, but there is no other test that will show this condition in the industry. It's the only one that will.
Mhm.
And if you have that condition and you haven't tested for it and it's too late, guess what? They call it an electrical failure. Well, something was wrong with the windings. They failed. You
Okay,
know,
his next question was based on the information, the FRSL should be
Mhm.
completed at the factory. Should it be completed at the factory?
It probably won't be unless you specify it.
Okay.
But when you go to commission your transformer, two things that are probably overlooked the most. One is doing a real good moisture assessment, okay, with your DFR test. The other is frequency response to stray losses. Now, we're really, really good at commissioning new transformers in terms of SFRA, because that's, common. What the industry thinks is that I moved it from point A to point B, and my windings can, shift or buckle, or, if it came on a rail car, they can, you know, bang the cars together and create, vibration and, shock. Um, but those are the two things that I think are really, really important, that get overlooked the most. And it's not that big a deal to incorporate that into your commissioning test. DFR and frequency response to stray losses, always done at commissioning. Now, if you're a customer purchasing a new transformer, you can certainly add it to your required testing at the factory. Um, and I would certainly recommend that.
Okay, great. And the last question is, do you need to shut down to connect the oil drying unit? And
No,
you already mentioned that.
nope,
No,
you do not. Yeah. It's has all kinds of safeguards built into it.
right. Okay,
Eh,
great. Great. Thank you for the presentation. Thank you, everyone, for those questions, and thank you for the great answers.